Now let us start looking into the systems. So first we look into the definition of the system. A system is defined as a mathematical relation which relates the excitement, that is the input signal, and the response, that is the output signal. Uh, Also we can say that a system extracts useful information from the given signal. So some of the examples of the systems are low pass filters, which mainly extract the low pass information from the given signal. So examples of the systems are y of t is equal to x square of t. This is a continuous time signal because it acts on the continuous time input and gives continuous time output. And y of n is equal to 2 into x of n plus 3. This is a discrete time system because it acts on the discrete time signal and gives a discrete time output. Let us consider a signal, sorry, let us consider a system y of t is equal to 3 into x of t. And suppose there is an input of x of t is equal to sine 3 pi t given to the system. Now we have to find the output. In this case, y of t is equal to 3 into x of t, that is equal to 3 into sine of 3 pi t. So this is the response of the given system for the given input. Now let us consider another system. Y of t is equal to e power x of t. Okay, and the system is given an input of x of t is equal to log to the base e pi t. Now we have to find the response of the system. Response of the system is given as y of t is equal to e power x of t, that is equal to e power log to the base e of pi of t, which is equal to pi t, because we know that e power log a to the base e is equal to a. So pi t is the response of the system for the given input. Now suppose there is a system y of n is equal to x of n minus x of n minus 1, and there is a signal x of n is equal to 0 1 2 given as input to the given signal. Now we have to find the output. We know that the output y of at n equal to minus 1 is equal to y of minus 1 equal to x of 0 minus x of minus 1. This is equal to 0. So y of 0 is equal to x of 0 minus x of, sorry, um y of minus 1 equal to x of minus 1 minus x of minus 2. This is 0. And y of 0 equal to x of 0 minus x of minus 1. This is also 0. And y of 1 is equal to x of 1 minus x of 0. This is by substituting n is equal to 1 in the given relation. This is 1. And y of 2 is equal to x of 2 minus x of minus 1. This is equal to 1. And y of 3 is equal to x of 3 minus x of 2. This is equal to minus 2, because this is 0 minus 2. From this we see that the response of the given system for the given input is equal to 1 0 comma 1 comma 1 comma minus 2. Here the value 0 corresponds to the instant n equal to 0. Now we will start looking into the characterization of the systems. One of the ways in which the systems can be characterized is linearity. So a system is said to be linear if it satisfies superposition principle. It means that if there is a linear composition of the inputs that is given to the system, linear combination of the inputs that is given to the system, the output given should also be linear combination of the individual outputs. Systems can typically be denoted by the relation y of t is equal to transformation of x of t. This is a generic relation. Suppose to the system there is an input x1 of t given, to which the output y1 of t is equal to transformation of x1 of t. And suppose there is an input x2 of t given, to which the output is y2 of t is equal to transformation of x2 of t. Now suppose there is a linear combination of the inputs given, which is a into x1 of t plus b into x2 of t, to which the output should be a into y1 of t plus b into y2 of t. If for the given input a x1 of t plus b x2 of t, we are able to get the output a y1 of t plus b y2 of t. It means that if we are able to get the output to this form, then we say that the system is linear. Equivalently for discrete time inputs, the response for a into x1 of n plus b into x2 of n should be a into y1 of n plus b into y2 of n, where y1 of n and y2 of n are outputs due to inputs x1 of n and x2 of n. So if this relation is also satisfied, we say that the given discrete time system is linear. So the obtained relations for continuous time and discrete time systems are analogous in nature. Now let us start looking into some of the examples as related to linearity of the systems. Suppose there is a discrete time system given, which is y of n is equal to sine of pi by 2 multiplied by n minus 1, which is as a whole multiplied by x of n. You have to find if the system is linear. When there is an input of x1 of n, the output of the system is y1 of n as a whole y1 of n, which is equal to sine of pi by 2 multiplied by n minus 1 as a whole multiplied by x1 of n. Similarly, when there is an input of x2 of n, the output y2 of n is sine of pi by 2 n minus 1 as a whole multiplied by x2 of n. Now, when there is an input of a into x1 of n plus b into x2 of n given to the system, the output y3 of n can be written as sine of pi by 2 multiplied by n minus 1, which is as a whole multiplied by a into x1 of n plus b into x2 of n. This can be rewritten as a as a whole multiplied by sine of pi by 2 n minus 1 multiplied by x1 of n plus b into sine of pi by 2 n minus 1 as a whole multiplied by x2 of n. We know that the quantities marked or quantities being marked are equal to y1 of n and y2 of n. So we can write the output as a into I1 of n plus b into y2 of n. So from this we see that for linear combination of the inputs, we got linear combination of the outputs. So from this, the system is linear. Now let us consider another continuous time system. Y of t is equal to x square of t. We have to find if the system is linear. For an input of x1 of t, the output is y1 of t is equal to x1 square of t. And for an input of x2 of t, the output is y2 of t, which is further equal to x2 square of t. When the input is a into x1 of t plus b into x2 of t, the output can be written as y3 of t is equal to ax1t plus bx3t whole square. This is the case because the output for any input is just the square. So for ax1t plus bx2t, the output is just the square of the same, which can further be written as ax1 square t or a square x1 square t plus b square x3, sorry, this is x2, b square x2 square t plus 2ab x1 t x2 t. So this wouldn't definitely be equal to a y1t plus b y2t. From this, we see that the given system is non-linear. Now, let us consider another example. Suppose there is a system given as y of n is equal to x of n multiplied by x of n minus 1 plus 2. We have to find if the system is linear. As before, for an input of x1 of n, the output is y1 of n is equal to x1 of n multiplied by x1 of n minus 1 plus 2. For input of x2 of n, the output is y2 of n is equal to x2 of n plus x2 of n multiplied by x2 of n minus 1 plus 2. So for an input of a x1n plus b x2n, the output can be written as y3 of n is equal to a x1n plus b x2n multiplied by a x1 n minus 1 plus b x2 n minus 1 plus 2. This is definitely of the form a y1n plus b y2n. So from this we see that the given system is non-linear. Now consider another system. Y of n is equal to n cube multiplied by x of n. We have to find if the system is linear. As before, for an input of x1 of n, the output can be written as y1 of n is equal to n cube into x1 of n. Similarly, for an input of x2 of n, the output can be written as y2 of n is equal to n cube multiplied by x2 of n. From this, for an input of a x1n plus b x2n, the output can be written as y3 of n is equal to n cube multiplied by a x1n plus b x2n, which can be deduced to the form a times n cube x1n plus b times n cube x2n. This can be written as a y1n plus b y2n. From this we see that for linear combination of the inputs we got linear combination of the outputs. From this the given system is linear. Now let us consider another system. Y of t is equal to x of t minus 3. We have to find if the system is linear. As before, for an input of x1 of t, the output is y1 of t is equal to x1 of t minus 3. For an input of x2 of t, the output is y2 of t is equal to x2 of t minus 3. When there is an input of a x1 t plus b x2 t given to the system, the output can be written as y3 of t is equal to a x1 of t minus 3 plus b x2 of t minus 3, which can further be reduced as a y1t plus b y2t. From this we see that for a linear combination of input we got a linear combination of the output. From this the system is linear. Now let us consider another system. Y of t is equal to 2 times x of t plus 3. For an input of x1 of t, the output is y1 of t is equal to 2x1t plus 3. For an input of x2 of t, the output is y2 of t is equal to 2x2 of t plus 3. When the input is ax1t plus bx2t, the output is y3 of t is equal to ax 2 times ax1 of t plus bx2 of t plus 3. So if we further reduce this can be written as a times 2x1t plus b times 2x2t plus 3. This is definitely of the not of the form a y1t plus b y2t for every a and b. So from this we see that for linear combination of inputs we are not getting a linear combination of the outputs. From this the given system is non-linear. Now let us consider another system. Y of t is equal to mod x of t. In this case, for input x1 of t, the output is mod x1 of t. For input x2 of t, the output is mod x2 of t. For any generic a and b, and for any generic x1 of t and x2 of t. For an input of a x1 of t plus b x2 of t, the output is mod of a x1 of t plus bx2 of t, which is less than or equal to mod a multiplied by mod x1t plus mod b multiplied by mod x2t. The right hand side quantity is equal to mod a multiplied by y1t plus mod b multiplied by y2t. From this, we see that for a linear combination of the inputs, we are not getting the linear combination of the outputs. From this, we can say that the given system is non-linear. Now let us looking into another way of characterization of the systems, which is time invariance. A system is said to be time invariant if delayed version of input gives delayed version of the output by the same amount. So in case of continuous time systems, if there is an input of x of t minus t naught, the output obtained is transformation of x of t minus t naught. This should be equal to y of t minus t naught. So using block diagram, this can be demonstrated as below. Suppose there is an input x of t, delay this by t naught, we get an output of x of t minus t naught. Now you feed it to the system t, the output is transformation of x of t minus t naught. Now, now take similarly feed the input x of t to the system first. The output would be transformation of x of t, which is equal to y of t. Now delay this output by t naught to get y of t minus t naught. If these two outputs are equal, then the system is time invariant. Otherwise, the system is time variant. Similarly, a discrete time system is time invariant if delayed version of the output is equal to output due to delayed version of the input by same amount, where here n naught and t naught are delays. Now let us consider some example. Suppose there is a system y of t is equal to x square of t. We have to find if the system is time invariant or time variant. When so in this case, the delayed version of the output is given as y of t minus t naught equal to x square of t minus t naught. This is by replacing t by t minus t naught. Similarly, the output due to delayed input would be y dash t is equal to, when the input is delayed by t naught, it is x of t minus t naught. So the output would be x square of t minus t naught. And these two are equal. Means the output due to delayed version of input and the delayed version of output are equal. From this, we see that the system is time invariant. Now, let us consider another system. Y of n is equal to x of 2n. We have to find if the system is time invariant. First, the delayed version of the output would be equal to y of n minus n naught equal to x of 2 times n minus n naught. This is equal to x of 2n minus 2n naught. Whereas for an input of x of n minus for a delayed input, so if the input is delayed, so the output would be y dash n is equal to x of 2n minus n naught. This is because the input is delayed by n naught. We see that the output due to delayed version of the input is not equal to the delayed version of output. From this, we see that the system is time variant. Now let us consider another system. Y of n is equal to x of n minus x of n minus 1. We have to find if the system is time invariant. So the first one, which is the delayed version of the output, y of n minus n naught is equal to x of n minus n naught minus x of n minus n naught minus 1. And the output due to delayed version of input y dash n is equal to x of n minus n naught. Here the input is delayed, so the input would be just n minus n naught. So x of n minus n naught minus x of n minus n naught minus 1. We see that in this case both the outputs are equal. From this we see that the given system is time invariant. Let us consider a discrete time system. Y of n is equal to sine of pi by 3n multiplied by x of n. We have to find if this system is time invariant. In this case, suppose there is an input x of n given, the output would be y of n. So the delayed version of the output would be y of n minus n naught, which can be obtained by replacing n by n minus n naught. So this would be equal to sine of pi by 3 multiplied by n minus n naught as a whole multiplied by x of n minus n naught. Now the delayed version of the input in this case would be x of n minus n naught. So the output in this case would be y dash n is equal to sine of pi by 3n multiplied by x of n minus n naught. We see that these two outputs are not equal, so the system is time variant. Here the delayed version of the output and the output due to delayed version of the input are not equal, so the system is time variant. Now let us consider another system which can be represented as y of t is equal to t cube into x of t. This is a continuous time system. We have to find if the system is time invariant. So here for an input of x of t, the output is y of t and the delayed version of the output is y of t minus t naught, which is obtained by replacing t by t minus t naught. So it would be t minus t naught whole cube multiplied by x of t minus t naught. Now, when the delayed version of input x of t minus t naught given to the system, the output is y dash t is equal to t cube multiplied by x of t minus t naught. Here just the input is delayed, so this factor t remains as is. Now, the output due to delayed version of input is not equal to delayed version of output. From this, we see that the system is time variant. Now, let us consider another system. Y of t is equal to 2 into x of t plus 3. We have to find if the system is time invariant. Here also the delayed version of the output would be y of t minus t naught is equal to 2 times x of t minus t naught plus 3, and the output due to delayed version of input would be y dash t is equal to the delayed version of input is x of t minus t naught, so the output is 2 into x of t minus t naught plus 3. We see that this is equal to y of t minus t naught. From this we see that the given system is time invariant as delayed version of output is equal to the output due to delayed version of input. Now we will consider another system. Y of t is equal to x of t minus 3 by 2. So in this case the delayed version of output y of t minus t naught is equal to x of t minus t naught minus 3 by 2, and output due to delayed version of input is y dash t is equal to x of t minus 3 by 2 minus t naught, and this is equal to y of t minus t naught. From this we see that the given system is time invariant. Now let us consider another discrete time system which is y of n is equal to mod of x of n. In this case the delayed version of output is y of n minus n naught is equal to mod of x of n minus n naught, and the output due to delayed version of input is equal to y dash n is equal to mod of the delayed version of input, which is x of n minus n naught itself. And this is equal to y of n minus n naught. Here we see that the delayed version of output is equal to the output due to delayed version of input. From this, the given system is time invariant.